Hey there, I'm SourceMake, and today I'm going to teach you about C++ classes and templates, and we're even going to create our very own custom C++ data structure. So as usual, I've got my website open and it's got all the details that we're going to need. And to be honest with you, this is going to be like a medium length video, maybe like 20 minutes. I don't know right now. So if you just prefer to look at the code yourself, go ahead and click the link below this video and you'll get to this webpage and it'll teach you everything you need to know. You can read it yourself if that's what you prefer. And yeah, basically I'm going to be walking you through some code to show you. First, we're going to do a simple warm-up. Then we're going to learn about classes. We're going to separate the classes into separate files. We are going to look at templates. And then we're going to see how to use templates to build our own custom data structure, which is a lot. So it's going to be a bit long, but hopefully you're going to learn a lot in this video because I'm going to explain it really well. And to demo this, I've got the code on my website, but I also have it uploaded on GitHub. So go ahead and click the link to GitHub below this video. I don't know if I mentioned it, but go ahead and subscribe to the YouTube channel while you're down there. But the code is on GitHub, and I'm going to be basically walking you through the code since I already have it written out. But I've got Linux open, and we're going to be running the code ourselves just to see how it actually runs, even though we're still going to be looking at it. So here we are. Let's just jump right into this. So C++ classes and templates in our own custom data structure. We're going to start off with a brief warm-up for Hello World and showing what functions are. So C++ program always includes IOStream, not always, but most of the time, and using namespace SED. We'll just take it for granted that we include this. The program starts at main, and the first line here is say hi. So we're calling this function say hi, and we're passing a string called sourceMake. And you can see the function say hi is right here. It's of type void, which means there's no returning, and it gets passed a parameter of string that is variable named name. And you can see our function does two things. It calls cout twice. It says hello world from the name, new line, and it says also hello world, new line. So let's run that really quickly. And I've got the code right here. You can see, but I've got makefile set up to do this for us. So you can see make is g++ main.cpp, run, and then we run the executable that gets generated, and hello world from source make also hello world. So hopefully you could understand how this code generates this output. And that was really simple. That's just functions. Now we're going to move up to classes in C++. So let me prep this. And let's get back to the website. So classes are next. Classes are basically just creating a blueprint. So most of the time they model objects, but we're not going to talk about object orientation right now at all. What we want to do is just make a custom class that is going to have some functions that are useful for us and also maybe some variables that are helpful if we need to use them. So let's walk through this code. You can preview it right now. This is what it's like. But let's look at the class code first. So I've separated the class into these little brackets. I like to do that. That's what my programming master does, so that's how I do it. And we've got this class called my math class, and it's all in wrapped. It's wrapped in here. So basically, it's going to provide a utility for some math functions for us, and we're going to start out our class by prototyping the variables that we're going to need, defining them now inside this class. So we've got a private variable named favorite number, and that's an integer. We've got some public functions. One is the constructor for this class. You can tell because it's the same name of the class, and it's got no parameters. We've got an overloaded version of this constructor that accepts one integer. We've got a void that is set favorite number and it accepts an integer. We've got an integer function to add two integers. And finally, we've got another function to print the favorite number, and it's of type void. But this time, you see we prototype these. What we're going to do for this particular function is we're going to define it inside the class function itself. And this is really bad. Don't ever do this, and you'll see why in the next section. But this is really bad programming practice. The good programming practice is to define the functions outside of the class itself. So you can see right here, we start defining our functions. The first one is my math class. We say my math class, which is the class name, and that's the scope that this function is for. And this is the constructor. What we do in this constructor is we set the favorite number to 7 by default. If we don't want to set the favorite number to 7 by default, what we can do is we can accept a parameter called fav, and we set the favorite number to fav when we initialize the class. So hopefully that makes sense. Constructors are just when you call a class, the constructor is called to set up your variables. And then you've got functions that are called whenever you call the function itself. So we've got this other function that's void set favorite number to fav, and you set the private variable, which you can access inside the function. You see that it's private. You can't access this if you outside of the class, but inside the class, these functions can. So favorite number, you set to fav. And finally, a utility function for add. Add these two integers, return the addition of them. Pretty simple. And now we've got some code to test this out in the main function. So we use our class by making an object of it. We say my math class is the type. Instead of enter bool or char, we say my math class, and we name it class1. So then we call the class's public methods by saying class1, and the method that we call is print favorite number. And this time, let's create a new class, but this time we're going to use the overloaded constructor, which is this right here, to set the favorite number to start out as 20. So this one should be set to 7 because we didn't specify anything. It calls this code. But this one, when we initialize the class, we say, okay, pass 20 to it, and it passes it to this constructor, and it sets our favorite number to 20. And we're going to print that. So we should see 7, then we should see 20. And then we've got this integer named sum that we're creating that is going to be if we use class 2's add function for 5 and 5. So what this basically says is class 2, which is this object, we're going to call the add function on it, which is this function. It's going to be passed 5 and 5. And what's going to get returned is 5 plus 5. So this should be 10, and we're setting that into the variable int sum. And then we're just going to print that out. So what do we expect? 7, 7, and 5? Is that what it says? No, 7, 20, and 10. I can't do math. Yeah, so the favorite number by default is 7. Then we initialize it to 20 this time, and then we're adding these two to be 10. So let's go ahead and do that. This is the exact same code that we just walked through, and this is what shows up. So we ran it, and it works. So that was classes on a basic level. Now, just for posterity's sake, we're going to separate the classes into 3 separate files that you can see right here. So normally, in that last example, we had the classes all in one file. This class was all in one file, but that's not really scalable. If your project gets too large, you can't do that. So it makes sense to learn how to separate classes into files like now. That's really useful, and you should try to memorize it. So let's do this from here, actually. Main.cpp is exactly the same. We're going to use this same exact code, but we're just going to move it around a little. And our main file is exactly the same. Not the file itself. The main code is exactly the same. The only thing that changes is this. We include a reference to this. So we created a C++ file, a .cpp file called myMathLibrary, and that's where our class code is going to live. You can see it's the exact same code as before. Everything that was inside those 2 brackets is in here now, and we just have the including iostream and the using namespace std because we were using those. So our class code is exactly the same. And what we have to do for this is a CPP file that gets compiled, but we need a header file for it. So, in C++, before you use a function, it has to show up above the code, in the code. So you can't use this unless it gets defined. So basically, we create a header file, and for classes, you just copy the prototype. So you copy this code, class my class, which is basically this exact thing. This little thing that we said before is what we do. And unfortunately, this should be like really neat, but because we defined this function inside the class, it needs to be defined inside the header file, which is bad programming. Never define the functions inside the class itself. Always do it outside of the class like we did here. So we've got this CPP file with our class code. Then we've got the prototypes of this, which is the class itself and the functions that are inside the class and the variables inside the class. And we are going to say in this header file, we use that as a prototype by including it, by saying include mymathlibrary.h in quotes. So what this line does is basically it takes all of this code and puts it right in here. That's what header files are. So that's what it is. You're just replacing this line with all of this code. And that prototypes it so that you can actually use these functions. And this is the exact same code as before. The only thing that's different is we have a header file now, and we've got this class code in a separate file that also has these two lines. Main has this line, and the header file is basically just the class code. That's all you have to do. If it doesn't make sense, which it might not because the way I'm explaining it, I recommend really looking at the code yourself. If you go to an example, you can see how it works. So let's make this, and it's the exact same output as before. So that's classes, and we're going to move on now. We just did that whole section. You learned about classes, and you learned how to use the exact same code in separate files. And now we're going to learn about templates. So let me just prep this by getting rid of this, and we are a quarter of the way done. More than that, 60% done. This next section shouldn't take too long. So now templates. So basically templates, we're going to look at the code for our example. The reason you would use a template is because sometimes you want functions to work or you want classes to work without worrying about the data type. So we've got two pieces of code as an example. This first piece of code, we've got three functions. It's a really simple file. Three functions called add. They're all called add and they're all overloaded. So this first one returns an integer and accepts two integers. It says, let me add integer A, let me add integer B, and I'll return the integer of their addition. This one says, double A and double B, let me return a double of these two being added. And this one is long A and long B, let me return the long of these being added. And this is kind of cumbersome, right? We have three functions for basically the same functionality. We're just adding it. It's just that the incoming data type might be different. So if you run this code, then it all adds up to what you expect it to be. But the magic is in templates. So a C++ template, you can see in this next example is you do this. You declare a template name, and you say template, the type name is T for a function. If you're using it for classes, this would be called class, and we'll see that. But if you're doing it for just a function, you say template type name T. That's just take it from me. That's what you do. And then the return type for your add function is T. And now you can use T all over. You can say, okay, the return type for this function is T, and it accepts a parameter of variable name A that is of type T. And it also accepts another parameter of name B that is of type T. So before we had, like, let's say long A and long B that returned long for this add function. We just say T add, TA, TB. Really simple. And this is the exact same main function as before, and the output's exactly the same. So just to reiterate this, templates let us use the same piece of code without worrying about the type of the variable. It can work for any type. And this is really powerful because it means we don't have to worry about like making a bunch of functions for every little variable type, or, you know, there are so many variable types in C++, int, double, long, even custom ones if you have like big integers and stuff like that. Instead of worrying about that, you just use a template so your code works for any variable type, and that's really powerful. And we're going to use this as motivation to make our own data structure. We're on the final level. So just to reiterate what happened so far, we did a brief hello world with functions. We looked at classes and see how we can make custom functions, and the class is basically a blueprint for functions and custom variable types. Not custom variable types, but like private variables. We separated that class code into separate files, and we looked at templates, which is going to let us use basically generic variable names instead of being specific about it for our functions. And now we're going to use these templates to make generic classes. So our own custom data structure, the final section. So have you ever seen this before? Look at this line right here. Vector of type integer, we're naming the variable myVec. If you've ever used vector before, this is how you initialize it. You say, we're creating a vector of type integer that is named myVec. And you specify the int here, but you don't have to. You can make it long, double, bool, char, string, whatever you need to do. And you know why this works? Why these little brackets happen? Because the people who made the vector library used a class template. And that's why templates are so powerful. If you want to make your own code in the professional world, or honestly, even if your own little projects, you need to learn about templates. So we're going to make our own stack class using templates. And it's actually a lot simpler than it looks. Look at this. This is just like a few lines of code. The other code was actually harder. So wait. Should I run this for you guys? What is this? Okay, let's run this and make sure that it works, just to show you guys. So we're going to make it works. So final section, the last boss, our own data structure. We've only got 2 files. And let's look at the stack file first. So we want to make our own stack data structure. I don't want to go into the details of how you would do this, but like being really efficient about it. But basically a stack is, like a stack of plates. One variable comes in, another one comes in and goes on top. Another one goes in, goes on top. And the variables just keep going on top. It's basically first in is last out. When you want to access something, what you get is the top of the stack. So it's like a stack of plates. The plate that's on top is the one you pull out first when you're trying to heat up dinner or something like that. And we're going to make our own custom stack as our own data structure. So what we need is IOStream, and we need the vector class because we're going to use vector as our underlying data structure. And you can see our class right here. This is our code. It's in a class file by itself. And that's just what we're going to look at right now. So let me make sure you can see basically everything. Okay, whatever. So a class for our stack. We say template, and instead of type name, we say class T for the class. So you see right here how we called vector and we specified that it was an integer vector. Well, we're basically doing the same thing, except when we call our stack, which is named source stack, we're going to be using like bool or int just like that inside of those angle brackets. And to do that, you need to say a template for the type that you're declaring of this stack. So template class T, class source stack. And let's look at the prototypes. We've got one private vector, which is going to be the data structure that holds our stacked items. So if we have a stack of bools, then they're all going to be stored in this vector. If we have a stack of ints, they're going to be stored in this private vector that we don't want the user to access. We're going to handle everything for them. And we've got a few public functions and variables that we want the user to use. So int size is the size of our stack. Really simple. We've got void push, which is to add an item to the end of T, which is the end of the vector. But for the user, that's really like they're going to push it on top of the stack. We've got void pop, which is to remove the item from the top of the stack. We've got T top. You see T, which is the generic type that we're using. So if it's a stack of integers, then T would be int. we've got t top, which is going to get the item that's on the top of the stack. And finally, we've got bool is empty, which is to check if the stack is empty. Really basic stack, really simple. And let's see how we define these functions. So the first one is integer. So let's see how we look at the functions first of all. We want to define this variable named size, which is actually a function. And we are saying we have to repeat this here. Template class t, we have to use that for all the functions. We're going to say the return type is integer. We're going to say it's part of source stack, and you got to use the angle brackets, and then you can say size. So this is a lot to take in. Let's do a quick comparison. You can see that above, when we did our class code, when we defined the function, we just said class name, extension of, and then we did the function name. But this time, instead of just a class name, since it's a generic class, what we need to do is we need to say, we need to specify that it's a template of class. We have a template and it's of generic type named t. We're saying that the return type of this function is integer, and we are saying that it is part of the source stack class that's going to be using this generic t that we declared when the user initialized the class. That doesn't make a lot of sense. I know it's really kind of stupid if you ask me, but that's just the way you do it. Just remember to include this and the return type, and include the name of the class followed by this angle bracket with the generic variable name inside of it, which doesn't have to be t. It could be template. It can't be template. That's a keyword. It could be, I don't know, my t, something like that, whatever you need. But we named ours t up here, and that's what we're going to be using for everywhere else is the generic variable name. So just to define these functions really quickly, size is going to turn the size of our vector. Push is going to push back an item on the vector. Pop is going to pop back an item on the vector. And you see we've got this little check that makes sure that there's actually items in the vector. So top is going to return the top item of the vector, the very last item. And we've got is empty is just going to check if this size is equal to 0. This is using a lambda function, which so this basically reads return if the size of our vector is equal to 0 is true, then return true. And if not, then return false. That's the lambda function. So really generic stack, but the magic is in these template declarations. And you can see us using the stack in this main function. The main function basically, you would use this just even if we weren't using stack. So let me, I'll explain this line in a second, but for now, just take it for granted that we're including our stack file, which is actually named sourcestack.t.hpp. But let's see how we use the stack. So first, we declared the class name was source stack, so that's how we have to declare it here. We're saying that the generic type is going to be bool, and the name of the variable for the stack is bstack. So bstack, we push false, false, true on top of it, and then while it's not empty, we are going to output the top of the stack, and we're going to pop the top of the stack. So we expect to see true, false, false, because false goes on bottom, then another false goes on top of that, then true goes on top of that. Next, we make an integer stack. Same declaration. The class name is source stack. It's of type integer, so you put them in the brackets, and iStack is the name of the stack. We've got a bunch of pushing, 5, 4, 20. We pop the 20, then we push 3, 2, 1. So we push 5, it's on the bottom of the stack. We push 4, that becomes top. We push 20, that becomes top. But then we pop the top of the stack, which is the 20. That 20 goes away. So now our stack is just 5 on the bottom and 4 on top. Then you push 3, push 2, push 1. So we expect to see 1, 2, 3, 4, 5. The exact same code as before, and that's it. That's how you use a stack. And let's go to Linux and make this really quickly. And I'll teach you a little secret. So let's make 100, which is true, false, false. Right? Where is it? Right here. Is this it? Yeah. True, false, false, which just outputs is 100. And you've also got 1, 2, 3, 4, 5. So the code works. And okay, now let me tell you the secret. So when we did the class code before, you could see, let me scroll back to it. You can see that we, in the main file, we created this header file, and then we included that header file in our main file to basically use the class code. So our class code was in this file named, what was it named? mymathlibrary.cpp. And then we created a header file for that to prototype it, and we named that mymathclass.h. And then we included that prototyping code in here so we could use the math library functions. But you see, when we use the generic type, you can't actually use this prototype in a header file. It just doesn't work. So what you have to do is you have to create a special file type named t.hpp. Honestly, I don't know if this t is required. I think that's just naming convention, but just the way it works. But the HPP file is basically a header file, but you're basically telling the compiler sort of that is code to be compiled, I guess. Normally an H file doesn't get compiled. It's just prototyping, but I don't know. It's just some magic that you use with templates. I'm not going to lie to you. It seems a little ridiculous, but just do it if you're going to do it. So again, our code doesn't have a header file this time in the separate file. What we did is we used a different extension, and then we just included that extension, HPP. So just to reiterate what we did today in this video, we made our own custom data structure, and that got built upon classes and templates. So I don't want to go over them again because we spent so much time on it. If you want to look at the code, I really do recommend clicking the link below this video and, reviewing it all yourself to see exactly how it works. You should also be testing this yourself. But yeah, we made our own custom data structure in C++. Templates help us use generic type so we don't have to declare the return type, or we can use whatever type we need to at the time. And classes are basically blueprints that let us define functions. So I'm SourceMake. Thanks for watching.